Hey guys, welcome back to a new video. Today we'll be learning how to solve this problem of finding the largest area rectangle in a histogram. Okay, so let's jump to the problem statement. So you are given n non-negative integers representing the histogram's bar heights where the width of each bar is 1. Find the area of largest rectangle in the histogram. So suppose you are given this histogram with these heights of the bars. Each bar is of width 1. We have to find the largest possible area of rectangle that can be formed with this histogram. Okay, so the largest area rectangle that is possible in this histogram is this one, which is of area 14. Okay, 2 is the height and 7 is the width. So let's see how do we solve this problem. So we'll be discussing a stack-based algorithm for solving this problem. This problem function accepts a vector of heights, which is the heights of the bar of the histogram. Okay, and it will return the maximum area that can be possible in this histogram. So we'll maintain a stack which will store the indexes of the bars in the stack, and this stack will maintain an invariant that the bars of the indexes stored in this stack will always be of increasing height. Okay, so let's see how this is going to work by going through a dry run through this code. Okay, so n is the higher number of elements in this number of bars, and I starts from 0, and we will continue till I reaches the end of, we'll process all the bars. Okay, so in the first element the indexes is empty, the stack is empty, so we basically insert the element here. Okay, the index of the first element here. Now I is at position 1, right? Now at position 1 we are checking whether the bar at the uh, top of the stack is less than equal to the height of the currently processing index. So in this case we are comparing 4 is less than equal to 3. Okay, which is false, therefore we end up here, right? So the top element is the top element index is 0. We pop this out. Okay, and we calculate the area with this formula. The formula is basically, if the stack is empty, then we multiply the top element, which is this one right now, heights dot top. So the top was 0, height of 0 is 4. This is multiplied by the number of elements that is currently processed. Okay, that is 1, right? So 4 into 1, this is basically giving the area of this bar, right? So we update the max area with this. So the max area is now 4, and I is at position 1, right? And the stack is empty. Okay, I'm going to erase all this. So now I is at position again we I still here, I is still here, and we again check if the stack is empty. Since the stack is empty, we are going to insert 1 here, right? Then we are incrementing I, so the I is now 2, I is here, right? So again we check if the stack is empty. No, again we are checking if the top element in the stack, which is height 3 is less than equal to the current element that is being processed 2. In this case also it is false. So we go to the else part. uh, we find the top index as 1. Okay, so we pop this out. Again we calculate the area using the height of the top element, which is this one. Okay, so this is 3 multiplied by, since the stack is empty, we will return the number of elements currently processed, which is 2, right? 3 into 2 is 6. Since 6 is greater than the max area, we update the max area as 6. Okay, so currently I is 2, right? I is still less than n, since n is 1 2 3 4 5 6 7 8. 2 is less than 8. We go again. The stack is empty, so we push 2 into the stack. Again I is incremented. Again I becomes 3. 3 is still less than 8. Now stack is not empty. We are checking this condition, whether the top element in the stack, currently this is 2, right? 2 is less than equal to the so I was here, so the 2 is less than equal to 5. Yes, it is true. So we push this I to the stack also. So stack now contains 2 and 3. Again I is incremented here. Still I is less than n. Stack is not empty. Again we are checking whether the top element of the stack, which is at position 3, this is 5, is less than equal to 6. Yes, so we again push the index of 6 to stack. Okay, so notice that the stack is containing elements in increasing order. So index 2 corresponds to height 2, index 3 corresponds to height 5, index 4 corresponds to height 6, right? So this is in increasing order. At least it will be in non-decreasing order. So now I becomes 5. We check whether stack is empty. No. We are comparing whether the top element of the stack, that is 6, is less than equal to 2, in which case this is false. So we go to the else part. Again the top index is kept in top. So the currently height of top is this, which is 6. And since the stack is not empty, we go to this part. This is basically the difference of the elements from the stack. We get the top index, which is 4. Okay, and then we pop this index out. So the 4 is popped, top index is 4, right? And then we find the area using a height of top. So the which is 6 multiplied by, since the stack is not empty, we'll go to this portion of conditional statement. Here I is 5 minus top element, which is at the stack right now, is 3, the index, minus 1. So what is this? The value of this is equal to 1. Basically this is giving from currently processed, uh, the element we are currently processing, to uh, this element. Basically using this bar as the minimum height, we are finding the maximum area possible uh, for this histogram. Okay, so we are finding the area of this, right? So this gives the area as 6 into 1 equal to 6. so max area doesn't change since it is still 6. Okay, now we go to the while here. So the I is currently 5, it is still less than 8. Indexes are not empty. We check now. I'll erase this, whether the top element, which is at index 3, erase this also. uh, so this is 5, height of the is less than equal to 2. So this is also false. We go to the else part. So the top index is 3. We pop this index out. So the index tree height is 5. Okay, 5 is the height multiplied by since the stack is not empty, we go to the else part. So I is currently 5 minus indexes dot top is currently 2, right, minus 1. So this is 2. So the 5 into 2 will give us 10. So basically we have found the area considering this element as the smallest bar. We are finding the area, so we will be finding the area from here to here. So the max area gets updated. Max area is equal to 10. So again let's see, let me clear this out. Again 5 is still less than 8. We go to this if condition. The stack is uh, not empty, so we go to this condition. So here the top element is currently this one. Okay, so the height of that is 2, which is less than equal to the height of the current element. So this condition is true, so we insert that index here. So 5 index with which has height 2 is inserted. Okay, again the index is incremented. We go to here, stack is not empty, and the height of the top element, which is 2, is less than equal to the height of the currently encountered element, which is 3. So again we push the element to the stack. Okay, then we check uh, I is incremented here. So this stack is not empty, and the current element at the top is 3, height is 3, and which is not less than equal to height of the encountered element. So we go to the else part. The top index is 6. We pop this top index and we calculate the area. This is the height of the top element, and this is multiplied by, since stack is not empty, we go to this condition. So I is currently 7 minus top element uh, in the stack is 5 index minus 1, which is 1. So 6 into 1 is 6. Since 6 is not greater than 10, we don't update the max area. Okay, again 7 is less than 8. Okay, stack is still not empty, so we go here. The top element is 5. We pop this element out. Okay, So the height of this is 2 multiplied by, the stack is not empty, so you go here, 7 minus, currently stack top is 2 minus 1, so this is 4, 2 into 4, which is 8. So this is basically, considering this as minimum, we find the height from here to, area from here to here, this area. Okay, so again, after finding this, since the max area is not updated, since 8 is not greater than 10, we again go to this while loop. 7 is less than 8, is stack is still not empty, and we check the height at the top of the stack, that is 2, is less than equal to height of the currently encountered element, which is false. We again go to the else, the top is equal to 2, so we pop this out. So the height of this element is 2 multiplied by, since the stack is empty, we find the total number of elements encountered, which is 7. Okay, 7. So this is equal to 2 into 7 is 14. So we update the max area to 14, right? Again, we go here, still I is 7, 7 is less than 8. Since the stack is empty, we push this index to stack, which is 7, right? And we increment it, so I becomes 8. 8 is not less than 8, so we break from this while loop, right? So stack has currently one element, index is not empty, the stack is not empty, top element is 7, we pop the stack. Okay, we find the area using the height of the bar is 1 multiplied by, since the stack is empty, the wheel I is currently 8, right? I is pointing here 8, so 1 multiplied by 8 will be 8. So we do not update the max area, and then we return the max area as 14. So notice that whenever we encounter an element which is strictly lesser than the uh, element at the top of the stack, we start calculating the area with the previous stack top element as the minimum element, the minimum height element. We calculate the area. So for example, when we encountered 1, so what we did is we consider from this previous element, we calculated the area till whatever stack top was there before this element. So this 5 was before 6, so we calculated this area, right? After we remove this, then considering this bar as minimum, and the previous stack top was 2, right? Previous stack top was 2, so we calculated this area. Okay, again we removed this element, then considering this bar as minimum, we calculated the area, right? In this way we are calculating the area whenever we are finding a bar which is smaller than the previous bar. Okay, after all the bars are exhausted, and I is um, after the last element, we see if there are still elements in the stack. If it is there, we simply find that area, like So with this bar as minimum, we are finding this area, right? So what is the time complexity? Basically, it's just a single loop from I is 1 to n. All these are constant time operations. And here also we are popping the stack till the stack is empty, which the stack can have at most order of n elements. Okay, so the time complexity is order of n. So what is the space complexity? The space complexity is also order of n, because we can have a case where the bars are in increasing order, right? So in which case we will keep inserting the bars. This while loop will keep inserting the bars. So the space complexity is also order of 10. Okay. I know it's a pretty difficult problem to understand at the first place. So I tried to do a dry run for this algorithm and show you the probable output of the problem. I hope this video helps you in some way. Thanks for watching. Keep subscribing and sharing the videos to keep me motivated. Thank you.